thermal fluid sciences experts. This is Pro Ready Engineer.
Well, hello again. This is Bassam Abdelnabi from Pro Ready Engineer. This is a much shorter video from the very long 2 hours video that I typically post. So if you like it, make sure to like and subscribe, and just consider watching the full video. Thank you and take care. Now let's move to the pumps. Why say the pump different? Well, you will know in a second that the fact that it is incompressible will have a simplification to the example and will make things taste a little bit different in a good way. So this is a pump. Pump needs work. There's something coming in. This is water coming in. There's water coming out. When the water comes in with a certain m dot. It has h, it has velocity, it has kinetic energy and potential energy. We killed that. M dot h v z2. Let's write down the energy equation, the generic one. Many things, there's no q out, there's no q in, there's no work out, it's only work in. And furthermore, we can neglect the potential energy, we can neglect the velocity difference, assuming that v1 and v2 are the same. That's an assumption. It may not be. By the way, it may not be. The potential energy difference makes perfect sense to ignore that for the pump. This pump, like if I have it here on the table, and it's like this big, this very large pump. And you look at the difference between, it's literally the immediate inlet. This is like the immediate inlet to the pump and the immediate exit of the pump. You say, well, these are very close. I mean, potential of what? Compared to this order of magnitude, this thing is moving tremendous amount of motor, tremendous amount of energy. It's many horsepower. It's like you saying, I have $10 million and 2.5 cents. That doesn't make any sense. You don't do that, right? You have that feel for the money. Please use the same feel for the energy. You say it just doesn't make sense. Don't talk about it. Good. So potential goes away, and I assume that the velocity is the same. That's an assumption again. You will see in a second that I will actually not use this assumption. But in this case, put everything together. Work of the pump is m dot times delta h. And you say, well, didn't we just do that with the compressor? We said the work compressor is m dot delta h. No, we're gonna take this to the next level now. Isn't h u plus p over rho? By definition is the enthalpy. Let's do that. So we plug it in. And there you go. Here's the pump equation now. So pump power is delta p over rho plus delta U. But what is delta U? U is the specific, is actually the enthalpy. Now the enthalpy for an incompressible fluid is CV times T. So that term becomes CV delta T. Well, delta T is the change in temperature. Now pumps, it's a very reasonable assumption to assume that the temperature did not change. So that CV delta T just goes away. There's no value of saying CV delta T. There's no temperature change. So suddenly something fascinating happens right here. The work of the pump is simply the delta pressure over rho. Amazing, is that right? Amazing. Imagine you have a pump sitting here on the table. Pressure is measured at the inlet and pressure is measured at the exit. There you go. Take this pressure, divide by the rho, and there you go. That's the work of the pump. If you really want to get the power drawn from the electricity, a little bit more formulas will need to come into this, but this is great. This is a great starting point. Just the knowledge of the pressure. Remember, in my properties video, pressure is a direct measurement. I just put that sensor right there. Easy going is the pressure, is the work. In 1 second, I get the work of the pump. Now try to do that with enthalpy. Enthalpy is not easily measured. It's not easy. It's not a direct measurement. You cannot do that. You cannot online measure enthalpy. So that's the goodness of making this simplification for the pump. It's something that we very easily measure accurately. Good.